Oh, thanks, man. Okay, so in this lecture, I'll be covering for loops. Wait, no. That's next lecture. Okay, so this lecture is going to be kind of a hodgepodge of just random DSU tricks that you can do, tricks and modifications. So I'll be covering each trick kind of quickly, and hopefully in the union of all of them, you get some good problems that you can solve. So, and this micro already doesn't work. Cool. So first, hopefully everybody knows what a DSU is. If you don't, this lecture will be recorded for you to watch again later. Stands for Disjoint Set Union. You might also hear it referred to as union find. Now, as a preface for this lecture, I kind of am operating under the assumption that you know DSU, but one thing that you might not know after even knowing DSU is kind of the square chart of the time complexities, right? So there are two things that make DSU run in time, or run quickly. There's path compression, and no path compression. Then there's also what I call the small to big heuristic, and then we'll have this for the no, right? So the DSU kind of maintains this tree, right, where every node has a parent, and the root of a component is the representative of the component, right? And so checking if two nodes are connected to each other is equivalent to checking if they have the same representative. Now, if you use this small to big heuristic, the idea behind the small to big heuristic is that whenever you join two components, you will point the representative of the smaller component to the representative of the larger component. And you can argue that for any node, the length of the path from itself to the root will be logarithmic in size, because the only time that the length of your path to the root can increase is if you were the smaller component during the merge, right? And being the smaller component during the merge would imply that after the merge, the size of your component has at least doubled, and therefore the path length is logarithmic. So we can say that even without this path compression that I haven't described, right, that this find operation you'll have to do is logarithmic. Now, if we use just, oh, I don't like how I did this. No, it makes sense, if we use just path compression, the proof of time complexity is quite a bit more difficult. And so I'm just going to leave that as an exercise to the reader, that if you use path compression, and in path compression what it is that you are essentially, every time you traverse to the root, you are compressing that path and saying, okay, don't take all these parent links one at a time, you already know where you end up at, right? And so that by itself is logarithmic. And then when you use both of them in unison, you get the inverse Ackermann thing, which is like O of 4 for any number that can reasonably be stored in a computer, right? And then here, there's just, don't ever do this, right? That's going to be linear time. Now, this wasn't a DSU lecture, right? This wasn't me explaining DSU, so if this didn't make any sense, I'm sorry. I'm mostly trying to preface the time complexities of the algorithm, because what's going to happen is in a lot of modifications to the algorithm, you're actually going to remove path compression. Because path compression relies on amortization, and a lot of these modifications to the DSU break with amortization. So what I'm basically trying to get across is that even without path compression, using just a small to big heuristic, you still have a relatively fast data structure for this problem, right? So while we are talking about small to big, I can introduce the first kind of trick. And the first kind of trick that we can use is a relatively common one, and it can solve, the most classic problem that it can solve, right, is you are given a graph with weighted edges, 9, 3, right? And what you want to do is you want to answer queries which are between arbitrary nodes in this graph, let's call this U and this V, right? If we were to traverse from U to V while trying to minimize the maximum edge weight that we take, right? What is that minimal maximum, right? Now, if this were one query, how might, like, you do this? Yes, Tyler?
Sort the edges, merge DSU as soon as the two components get connected. Like, that's your largest edge on the path.
Yeah, awesome. So we can use like a greedy argument, right? Which is one by one, consider the edges in smallest order, right? And as we are adding these edges to the DSU, as soon as we have enough edges to connect the two nodes that we are querying, right? Once they're connected in the DSU, we can stop. We know that that is our answer, right? Now the issue comes about when we have 10 to the 5th queries, right? Because you can't check 10 to the 5th queries each time. So what we can do is in the DSU, we can kind of, for each node, right, for each endpoint of the query, we're going to store like a vector of sets. And like the way you implement this might vary, but I'm giving kind of like the most perhaps understandable most understandable implementation, right? And so what we can say is for each query, we have its UV, and we'll say its answer index, right? Some place where if we were to answer this query, we'd know where to put the answer, right? So what we can do is for each query, if this is U and this is V, we can add a copy of this query to some set-like structure, which will probably literally be a set. And what's going to happen is we still process these orders from small to big. But that's just a sorting order, right? So that's the edges that we will add to the DSU one by one. Now, what we can do is every time we connect two nodes in the DSU, right, we have their two sets. And what we're going to do is for the node with the smallest set, we will first query, basically for every node, for every query in the smallest set, we'll query, is it also in the biggest set, right? Because if we've gotten to this point where we're adding this edge and we're saying, okay, there's a query that we've placed, the two endpoints of the query. If we have that situation where it's in both sets for the representatives that we're joining, right, then we can erase that query. We know the answer, which will be just the weight of the edge we're adding, and we know where to store it, right? And we can erase that. Now the issue is for the times where it doesn't, for the queries that don't get deleted, we have to kind of push them forward down the line to answer them later, right? And so you can get this kind of icky feeling that you might have to push queries up very often. But what we can do is we can rely on the same small to big idea that kind of makes the DSU work, right? And we can make the argument that if we're always merging the smallest set into the biggest set, right, then the number of times that any element will be moved will be at most logarithmic, right? And so now we can kind of answer all the queries offline in like Q log and like squared, because we have like a set log and we have a this might be like some factor of Q, but Q log squared, we have a log for the set and we have a log for the small to big, right? And you might be able to remove one of those logs with like some fancy implementation. But that's like the first kind of DSU trick. That's a relatively common one. A lot of times this small to big idea you'll use a lot on trees without DSU, but the idea can be adapted to be used inside certain DSU-like problems, right? So, okay, trick 1 done. Now, trick 2. This we kind of glued some stuff onto the DSU, right? We removed path compression, just because. Okay, sorry. Let me get back to the next trick. So, DSU rollback. So, DSU is a data structure that really likes adding edges, right? The whole point is that you can add edges to your graph quickly, maintain component information about connectivity, size, etc., right? What DSU really doesn't like is removing edges. So there are a couple of ways to deal with removing edges, and the simplest kind of sub-problem for removing edges is imagine a situation. Well, actually, I'll give you the motivating problem first. Imagine we have a graph, and this graph and this black marker is bad. So imagine we have a graph, and this was a problem I was going to write for SICamp, but never ended up writing, where many of these edges, or maybe not many of these edges, an arbitrary number of these edges will be colored gray, and then the remaining edges will have a variety of colors. Some of them will be blue, some of them will be, say, brown, right? And we'll say, because this is a competitive programming problem, that the color of the edges is represented by some number, right? And I want you to answer, given this existing graph, right, answer queries which are, I'm not sure why I'm writing the word answer queries. You want to say, given two nodes U, V, and a color C, right, are U and V connected if you consider only the graph that has all of the gray edges, as well as the edges of this color, right? So you're given the graph in the beginning, and then you're going to answer a bunch of these queries, right? So
how many colors are there?
There are 10 to the 5th nodes in the graph, 10 to the 5th edges. We can assume the colors are like 1 to 10 to the 9, but you could just coordinate compress, so it's like, it is what it is. Okay, so yeah, colors will say up to 10 to the 5th, because even if I make them arbitrarily large, you can coordinate compress, right? Or reasonably arbitrarily large. So how might we approach this problem? Well, first of all, let's make a DSU that only has the, I'm now realizing that we're going to make the DSU that only has the gray edges, right? So we have our graph that only has the gray edges. Now, one approach to this problem that you might consider is for each query, for each color, I mean, right? We can bucket our colors, or our queries, by color 1, color 2, color 3, right? And like, even though some of these colors will have a lot of queries, we know that across all colors, the sum of the queries is going to be however how many queries I gave you, right? So like, if we can have some behavior that doesn't mess up when you have a bunch of small dispersed colors, that's kind of our goal, right? So what we can do is, the naive approach would be to make your DSU starting from scratch, right, each time, add all the gray edges, then add all the color edges of C1, right, answer all the queries, throw their answers back into the answer array and call it a day, right? Then you rebuild the DSU from scratch, add all the gray colors, add all the gray edges, add all of C2, and then do the same process again and again and again. The issue with this is that if there are, say if half the edges I gave you out of my 100,000 are just the gray edges, you have to rebuild that each time, right? And that would be really bad if I give you, like, let's say 50,000 gray edges, and the rest of these colors are very, very interspersed, right? So you have to rebuild this baseline graph each time. So what we can do is we can actually build this baseline graph in the beginning, right? And we'll call this like the starting point. And then let's add these edges, these C1 edges for the first color, right? After adding all the C1 edges, we answer all the queries, right? Because we also have the queries bucketed in some other array. But then we need to get back to this gray version of the DSU without completely rebuilding it. So what I state, right, is because of the way the DSU is structured, the DSU, right, consists of some size array, which keeps track of the component sizes, and some parent array that keeps track of the parent sizes. And every time you add an edge to the DSU, what are you changing? Well, you have your size of U, where I consider U to be bigger, plus equals size of V, right? And you have your parent of V equals U, right? So you're redirecting the one root towards the other, and you're also making this change to the component sizes, right? So what you can see is that there's actually a constant number of changes to the array. And so what we can do is, for each of these changes, we maintain a, I brought on a space. We maintain a stack of these changes that goes, I have made a change to this index, size, like index, the parent, this index, right, PV index, right? So you'll store 4 values of the index that you're changing in the size array, the index that you're changing in the parent array, the previous value that it was before you've made this change for both of them. So that's 4 values, right? Now what you can do is you can keep this stack of changes. And what that means is that if you want to undo the most recent change that you've made, you can pop the top change off the stack, undo, right? So you reset whatever size was to what you say it was in your stack, and you reset whatever parent was to what you say it was in your stack, and then you move on, right? And so it will undo, it will roll back the changes one by one. And so that's what we can do for this problem, is we can create our baseline gray graph, add all the colors for C1, answer all the queries, because we also have the queries bucketed, and then just roll back just these most recent changes, right? And what that would mean is you're going to add and remove each edge like twice. And so this will amortize over all the queries so that you can answer all the queries. Does that make sense? One thing I didn't add is that in DSU rollback, right, as part of this stack idea, we don't need and really don't want path compression, right? Because path compression is an amortized situation where, you know, it takes all these parent to parent, node to parent edges, and it, like, you know, compresses them, right? And so if you have path compression, not only do you need to store the change you made to your parent, but you need to store every single one of these changes that you've made, right? Because you're going to reroute every single one of these nodes to the actual root. And so what you can have is you can have a case where someone will kind of force you to highly compress a path, right, where you store all of that compression in the stack, and then it will undo that compression, which means now you have to undo all these changes.
If you're using small big one, that'll still be logarithmic.
It will still be logarithmic. That's why we can still use rollback. Well, that will still be logarithmic, but what I'm stating is that it's not actually, if in the worst case scenario, the amortization doesn't help.
Okay. Another question regarding the size. So without path compression, what's the largest stack size you can get to?
Logarithmic. No, what are you saying?
So what's the biggest size that your stack needs to be if you're not using path compression?
The stack of changes?
Yeah.
The changes. Like it's for each change.
Yeah, but like how big is it? Like is there an order of the size of the stack?
Like what's your memory going to be for the stack?
It will be
because it is like logarithmic number of operations, you said, right?
no, it will be you're making one change, right? And the maximum number of changes that you can make in the DSU. So you can avoid adding to the stack, kind of, if you don't have an edge, but you still need some sort of, like if you try to add something where the components are already connected, but you would still need some sort of flag to say like undo this and don't make any undos. So really it's just O of changes you've made to the DSU.
And what is, isn't it O then because you can only merge the sets n times?
So you can only merge the sets n times, but like you have to still say, depending on how you implement it, like, hey, I didn't change anything, right? And so like you wouldn't need, say, 4 values, you might only need 1 flag, but like in the complexity, it's still like of edges. You might, if you like do it fancily, be able to avoid that because you can like. I wouldn't. I would just store it. But
I have some problems where you have to undo edges that like don't actually change the DSU.
yeah.
You don't have duplicate edges, you can store what the edges are.
Say again?
If you don't have duplicate edges, you can just store what the edges are and then not do
No, the
anything.
problem is some edges don't do anything. You need to like keep track of that information too. Like even the duplicate edges, like you have to store that the duplicate edge didn't change anything.
Yeah, but if you just store what the edge is, then you'll know to skip that duplicate edge.
But that's still storage. Like you're still storing.
Or
Like-
sorry, I said if there's no duplicates. So you can do this as duplicates, but like if there's just
But it's not necessarily duplicate edges. It's any edge that doesn't connect a component because it's already connected. So like but also
But
like
you only roll back the first one if you roll back the second. Like we can only do it one at a time. So we can just skip that one unless it was an edge that actually changed something.
but you are rolling back all the edges that you add, right? So the edges that you add in the graph are not necessarily the same as the edges you add in the DSU. So if you don't add that information in the stack about how you haven't made a change, then what you could do is when you roll back, right, you can accidentally roll back like too far because you have skipped an edge that you haven't made a change to the DSU in, but was added in the graph. So you need some sort of information to say, hey, I didn't make a change in the stack.
Or just don't keep like the initial DSU. Or just keep the initial DSU. Instead of rolling back, you have a copy of the initial DSU, and then you will use the same initial DSU.
But you have to copy the whole thing.
Yeah,
Yeah, you have to make,
There's a really complicated way to do that, but it's
which I'll get to if I have time. Okay, so I'm going to move on. If we have more questions about DSU rollback, I will answer them after the lecture. So the next kind of trick that I'm going to go over is, how's my time looking?
you have 30. Well, how long is the lecture?
An hour? Okay. So,
35 minutes.
It's
Cool.
been 23 minutes so far.
hey, that's good. I've covered the easy stuff in 23 minutes. Okay. So the next trick we're going to talk about is rollback, of course. Is onlineness checks. Or onlineness by partake checks. Also, as a kind of piece of information, there is a problem, right? So what I've just allowed us to do is undo the most recent change. There are problems where you want to add edges and remove edges interspersed, right? Like arbitrary queries. And you can imagine this is like arbitrary queries. And so there is a solution to this, right? I know how I mentioned that removing edges from a DSU is hard. The keyword is hard, not impossible. You can do this problem of like interspersed adding and removing queries with something called dynamic connectivity, right? And so I will not be covering this in my lecture today because Sachin will be covering kind of a more general form of this called dynamic divide and conquer on time, which is like a lot of people call it a dynamic connectivity trick. Why did I say dynamic offline? I meant dynamic connectivity. And so if you guys want to like learn that early, I can teach that at some point outside the lecture. Yeah. So yes, that is one of the biggest DSU tricks, but in order to not double dip on material and to be efficient in our lectures, we're going to save that until next week. Hopefully it doesn't show up on the set today. So the next trick is the bipartiteness. Bipart, I don't know how to spell. Check. Right, so we can define a bipartite graph, right? You guys usually see it in like this kind of structure, right? Where there are some edges on one side, some nodes on one side and some nodes on the other, and the edges always cross this imaginary line, right? No edges go between nodes that are on the same side. Another way to say an equivalent definition, right, is a bipartite graph is one that you can color the nodes such that no two adjacent nodes have the same color, right? And not all graphs are bipartite. The smallest example is this graph right here. There's no way for me to color these nodes such that two nodes are not connected and share the same color. And the underlying kind of condition that you can use, right? Well, first of all, easy way to solve this problem. If you just need to check if a graph is bipartite, we can actually do this greedily, or two-colorable. If I use the words bipartite and two-colorable, they're interchangeable, they're the same thing. We can do a kind of BFS from some arbitrary node, color that, let's say, black to start with, color all of its neighbors white, because they have to be, by definition, then color all of those neighbors black, and at any point you get any sort of contradiction, right, where I have colored this node black, I have checked to color all of the neighbors of this node, but one of them has already been colored the same color that I am, right, then that is a contradiction, right? And so you can kind of use like a greedy idea to do that check. The problem that we're going to try to do, right, is to do this check of bipartiteness, but I want to be able to add an edge to the graph and say, is the graph still bipartite? Add another edge to the graph. Is the graph still bipartite? And keep adding these edges. We can't use the BFS idea that I already erased, because any edge could change the bipartite nature of the graph, right, or could at least toggle it from being bipartite to non-bipartite, and you'd have to rerun the BFS each time. So instead, what we're going to do is we're going to do this with a DSU. Now, there's a very annoying way to do it with a DSU, and I'm still going to vaguely cover it. The kind of idea is that for a graph to be bipartite, right, what we can say is that if the graph is bipartite, then between the two nodes that we are now going to add an edge to, the path length of the already existing path between them that is like lost to the wind but still exists in the DSU, well, if you add this edge and the path between them before the length of it was even, right, then adding this edge will make an odd cycle, right? And so when you add an edge to the DSU, you need to basically essentially try to figure out what is the path parity, the path length parity between these two nodes. Proof left as exercise to the reader. Well, like, not even though, because like, what you can do is you can say remove every like other edge in the graph, right? And like the greedy coloring that you would necessarily need to do will make this the same when they connect, right? So like if any subgraph of the graph is not bipartite, then the graph is also not bipartite, So we can just only consider the odd cycle, and call it a day. Yes.
So is it true when graph becomes non-bipartite, it will always remain non-bipartite?
Yes. Yes. So we're only adding edges for now. Yeah. So what we can do is, if we can somehow maintain for every node the parity of the path length from this node to some reference node, right? Some arbitrary reference node. What I will argue that is that in a bipartite graph, there is no way to change the parity of the path, kind of by definition, because the only way that you could change the parity of the path from U to V is by finding some odd cycle. And so what I'm going to say is that all paths between U and V are the same parity if the graph is not bipartite. If the graph is bipartite. Once it's not bipartite, all these conditions, like, everything goes to the wind, but by that point you're already like kind of done and have solved the problem. So what we can say is that let's just find the parity of from this node to some arbitrary reference node, right? And if we do that for both nodes, then we can kind of XOR their parity to find the parity of the path. And then if the parity of that path is even, then adding this edge will make the odd cycle. Now what do we do for this? What do we use for this arbitrary reference node? Well, the thing that we're going to use for this arbitrary reference node is actually the root node of the DSU component, right? The already the representative node that we're maintaining in the DSU, right? So now I said I wasn't actually going to go over this because there's a better and easier way, but I will vaguely mention the way to do it, right? Is if we let's just remove path compression because adding path compression is annoying. What we can say is that if for every node we have the parity of this node to its parent, right? We have a parity array. Then during our find function, right? Parent in the DSU. I guess I have to. I will address that. Specifically, right, the word parent doesn't actually make any sense in the context of a general graph, right? Kind of. Specifically, what I mean is that we are maintaining for the path from U to its parent, right, that exists in the actual graph, right, not the underlying DSU graph, what is the parity of that path? That is what this parity array is maintaining. Now, what we can say is that the parity of the path from U to the representative, right, will now be the XOR of all these links up the chain, which will only be logarithmic because of the DSU small to big heuristic, right? And so you can path compress that, but really I wouldn't. It's annoying. Now, once we have that parity array, what we can say is when we add an edge between two nodes, right, between two actual nodes in the graph, and we have their representatives right here, right? When we add an edge between two nodes in the graph, in the DSU, we'll be adding an edge from this node's representative to the V representative, right? Oh, yeah. And so what we need to know is we need to know what is the parity of the length of the path from the representative of U to the representative of V, right? Well, what that's going to be is it's going to be the parity of the path kind of from the representative of U down to U, across one edge to connect them, and the parity from V to the representative of V, right? We have this information that we're maintaining, right, in the parity array. And so, because this is what we need to compute to figure out the parity of this connection in the DSU, right, which is what the parity array is storing. And so after each connection, we can store this parity information in the parity array, right? and then what we can say is if we add an edge to the DSU between two nodes that are already connected, right? Because the only time that you can make a graph not bipartite for the first time is when you're adding a cycle. Then you get this information of what is the parity of the length by going from UV to the shared representative, right? And then if both of these parities are the same, then you know that adding the edge will be make an odd length cycle. And so that's how you can do bipartiteness check in a DSU with edge additions, right? There is another way of doing bipartiteness check, which I would argue is a lot easier to implement. Thanks, Sandy. It's a little bit harder to kind of prove and show. It kind of uses two SAT ideas. So what we can say, right, the whole point of this bipartiteness is to be able to say if it's two colorable, right? So what we'll do is we'll have this split node concept of the white version of the node and the black version of the node. And then when I have an underlying graph, 1, 2, 3, 4, how many nodes did I draw? 5, right? When I draw an edge between 1 and 4, well then, okay, we're going to say this is 1 to 5, and this is 1 to 5, right? What I'm going to do is I'm going to draw two edges in this graph. I'm going to draw one from the white version of the node to the black version of the node, as in the white version of U to the black version of V, and then another edge from the white version of V, black version of U. I noticed in my speaking, I said 2. These are undirected edges. So that was just these aren't directional because they're DSU edges. Now, what we can say, kind of by implication, right, is that if in some way there is some indirect connection between V and the other color of V, right? If in some way these are connected, well, that implies a path that can traverse, start at V being white, right? And go to some other node, switching color, switching color, switching color, right? And end up at the same node, but a different color, right? And the only way you can do that is if there is some odd length cycle that will allow you to change your parity, right? And so what you can do is after each one of these edges, after each time that you add these, what's it called? After each edge you add, you kind of check the connectivity of the U and V, white U and black U, and white V and black V nodes, see if they're connected, see if any contradiction was made, right? And so that...
So you need to check both U and V, or is it sufficient to just check one or the other? 2 times extra memory, or that doesn't really matter, I guess.
It doesn't matter, and I would always check both. I do think you
only need to check one. Because if you add an image, then the cycle you created to violate it is going to include both U and V.
Yeah, I think you can...
Yeah, because it's like a symmetric graph.
Yeah.
Yeah, so you only have to check...
It's like the same argument for why you would only have to check U or V to begin with.
Yeah.
Because you're invalidating everything on the cycle, not just...
You're invalidating everything on the cycle, and you're also invalidating everything the cycle is connected to.
How do you prove edges?
You don't. But this would be a lot easier to slot into dynamic connectivity than the other one. So honestly, I would always do it the second way, but I thought the first way was still constructive. Yes, sir.
So for a second way, you could do path compression.
Yeah.
Do you have a use case for this, that forces online? Because offline you can always do the binary search.
Well, oh, you're saying, well, the actual use case of this, well, first of all, there's problems that force online behavior, right? Second,
That's what I'm asking. Like, do you have a problem where that's forced?
do I have a problem with that's forced? No, but I do have a problem where you slot this into dynamic activity, which
Fair.
is basically
I guess that's the answer. Is if you need dynamic.
if you need
connectivity,
it's like yeah, there's a lot of solutions to this that like maybe doing it offline would be easier, but there are expansions where you basically slot this into another thing that I'm either going over or Sachin's going over, that then having this online behavior is really necessary
Well,
and
there was
useful.
also that one problem with the like biparsec components that you like keep track of like how many components there are in the biparsec graph. And like, you can't really do that offline. Really. Like, if you have
Yeah, you could do component stuff like how many ways are there to two color the graph, right? Okay, so I think the next thing I'm going over is partially persistent DSU. So persistent DSU. So this, did I spell that wrong?
it's close enough.
It's close enough. Okay. Yeah, we'll just P. There we go. Oh, I'm sorry, I shouldn't have done that. Anyways, so for partially persistent DSU, right, the name is completely pointless. And I don't like the word persistence because I don't think it's descriptive. So instead, we're going to call this a DSU that can time travel. And so what we're going to say is I want a DSU that I can add edges to as one as one does. They add edges to the DSU. And I want to be able to query not just the most recent version of the DSU, but any past version, right? Now, we already have a version, like a way to do this, which is rollback, right? I could roll back to that past version and call it a day, right? The issue is that the rollback takes like O of however how many changes I have to undo, right? I want to be able to like teleport back. I want to literally be able to time travel back to that past version of the DSU without without undoing all those changes. So what we can do is we can actually store a separate I was going to call this a separate time travel array, but that is definitely not a good name for it. Last time array, right? And what this is going to do is, remember, we already have a size array, a parent array, right? And so I'm going to add one more array, and this array will store for each node when was the last time, right? Time is in like last update that was made, that it was the root of the when it was the representative of the component, right? So in the beginning, right, every node is the representative of its own component because every node starts off as a singular node, right? And then when you add one edge to the graph, well, this like node that is still higher will still be the what's it called? The representative, right? But we will change this guy's last time he's the representative value to be the time that this edge was added. Yes?
I think a more intuitive formulation is what time do you get a parent?
What time do you get a parent? Sure. Do we agree that they're equivalent though?
Yes, they're equivalent.
Yes. So if anybody likes that, then we can use that. But what we can now do, right, is essentially when we are trying to check if two nodes are connected, right, since connectivity of two nodes is equivalent to two find calls, right, we're finding the representative of U, we're finding the representative of V, we're checking if they're the same, what we can say is during this find operation, right, we're going to pass in the time that we want to consider, right? And so this is another one of those problems where you kind of have to remove path compression because path compression breaks everything, right? but we still know that without path compression, the number of jumps one has to take is logarithmic, right, because of small to big. So what we can do is we can traverse up the tree, up the DSU tree, and we only keep going to the parent if the time that we're passing in, right, is later than the time when this node becomes, or it stops becoming a representative, right? And so we're going up to that point, and that is the representative of this node at that time in the DSU. And then we can do that for both nodes, and we can get these representatives at this certain time that the DSU was at, right? And then to just keep track of this time array, right, you will do it in your join function, and your join function might take like a time parameter or some like incremented time global or structurally global variable, right, and it will make this change to the node that is getting a parent. Does that make sense? Now what this allows us to do, right, and the cool part about this is consider just the problem I said before, right, which was for every node, or for a graph, for a arbitrary weighted graph, 5, 6, 2, 8, 3, right? We can order the edges, right? And one can, and a lot of people probably do some form of parallel binary search on the DSU, right? Let's assume I've tied your hands behind your back and don't allow you to do like binary lifting or some of the other 700 ways to solve this problem, right? Is a lot of times you might parallel binary search this DSU to like find the first time that two nodes are connected, right? Well, what we can do now with this partially persistent DSU is remove the parallel in the binary search, right? Now we have a version of the DSU that we can like just regularly binary search, and it will allow for these arbitrary like random kind of queries that the binary search will want, right? And so that's how we can kind of use this. It allows you to like remove the parallel in the parallel binary search for a lot of like DSU problems that you might use it for. Now, notice I said partially persistent DSU, right? That's because technically there is a fully persistent DSU, right? Now, if you guys are familiar with persistence, you know, like in the form of persistent segment trees are the most common, right? That would allow us to make some copy of the DSU, of the underlying graph that DSU is representing, you know, store it, and then, so this is copy 2, right? And then make changes to this copy and make this like branching web of changes to different versions. Yes. A multiverse of different versions of the DSU where you're building off like different branches, right? And so the kind of trick to how to do this, and if it's ever useful, because this is like kind of absurd, is, well, we know that a DSU is built off of, at least conceptually, at least two arrays, size and parent, right? You can merge these into one array. I know Cactal does. I know people have been telling me to do it for years, and I absolutely refuse to. At least conceptually, there are two arrays that represent basically all the information of the DSU, at least the connectivity information, right? And so if we could somehow build the DSU off a persistent array, right, some array that you can make changes to, like make a copy of the array quickly in logarithmic time, make changes to that copy and have each of those, then you would then have a persistent DSU, right? And so how do we make a persistent array, right? Well, if you're familiar with persistent segment trees, a persistent array, right, is exactly a persistent segment tree, but you remove your range query function, right? The same behavior that you need, you do the CAM classic, which is point update, point query, right? And now you have a persistent array. If you are not familiar with persistent segment trees, and that doesn't make any sense to you, I can explain that after the lecture, but I find that that would be too much of a diversion into what this lecture is supposed to go over to explain that now. So that might not make full, complete sense. It's like, what is a persistent segment tree? That's okay. I can explain that another time. So we can do a full God tier persistence DSU, but it's like slow because you need to build it on top of a persistent array. Yes?
For the fully persistent DSU, you don't need the last time changing agent for the that you.
Yeah, no, two completely separate things.
Sorry.
Yeah. I would argue the partially persistent DSU is probably a lot more useful because it's like one line of, like 2 lines of code you have to add and gives you a lot of abilities. The fully persistent DSU I just mentioned because it's easy to explain to people that are ready to understand all the underlying stuff you need to know before it. Okay. Now I have 10 minutes. I am going to go over, and you were going to accept that. Thomas trick. This is Thomas with a Z at the end. Sadly, I did not invent this trick. But maybe we'll call it Thomas trick after this, because you will learn it from me. Okay. So, let's consider a very awesome problem called keyboard queries. True! Yeah, but faster and easier solution. In this problem, we have some, we have some, like, not hidden array, but some array, some string. I was going to say array of characters, but I think a string is probably a more representative thing, right? And what we're going to say is, what we need to do is there are going to be queries, and the queries will be of the form of the following. If it's of type 1, we're stating that this LR range is a palindrome. It does not tell you what palindrome it is. It just says, hey, this LR range, you are a palindrome. Query 2, is this LR range, and then this L2, R2 range, are the substrings equal? Now, there's actually 3 responses. There is no, yes, maybe. Okay, so can anyone give me a reason why answering no is actually really easy?
Substrings with different lengths.
Okay, why is that the only case?
Because if there's some range of values, like the only way you don't know if they're equal is if there's some character that can be like multiple different things, and then that's like.
Yeah. So I state that the array is all A's. All of these will be satisfied. The only time that the strings can be not equal is if they have different lengths, right? So the actual problem is determining, is it yes or is it maybe, right? This is like a case that you can just case out immediately. So what we kind of have to do, right? Well, what I want to do to solve this problem is I want to maintain some equivalence classes for each index of the array, right? And so, like this palindrome check, right, gives you a lot of information, right? Because if I tell you LR, right, you know these 2 nodes are equal, you know these 2 indices are equal, etc., right? And then if you have some like intersecting stuff, well, this like equality is transitive, right? And so you can make an equivalence class for each index, right? If you had some form of DSU, like if you had a DSU that you could do this update to, then after each of these palindrome checks, you could store the equivalence classes of each node, right? Some ID, and then maybe like do some check of if the substrings are equal, like if all the substring equality basically means like, is the equivalence class of these first two indices equal to the equivalence, like are these two equivalence classes equal, and then also are these equal, like pairwise, right? Now how do we do that? Well, first of all, we remove the palindrome part of this problem, right? And what we're going to do is we're going to turn this is palindrome into, well, we're going to store the string st, and then the reversed string, reversed, right? Like copied over. And so what I can say, if I can somehow solve this subproblem, right, which the subproblem now is what Thomas trick actually is I want to basically be able to go, this range is equal to this range, or not equal, but pairwise equivalent, as in this node is equal to this, right? I want to somehow perform all of these equivalencies, right, for each query. And then what we can do to actually, like, wrap back the palindrome part is, well, this is the reversed array, so we can actually just do the DSU connections ourselves of this, right? Does that make sense? Because if I say, hey, this string is equal to this reverse string, these edges that we had ourselves without Thomas trick are now guaranteeing the palindrome part, right? So this is what I actually want to solve, is this problem of given two ranges of the same size, make this DSU equivalence class, this DSU of equivalence classes connecting, pairwise. So how do we do this? Okay. So what we can do is consider an IMQ style trick, right? Which is, instead of taking this range and saying it's equivalent to this range, I'm going to find the largest power of 2, right? So say this is 15, right? I'm going to actually split this into two 8s, right? I'm going to split this into two queries, basically, where I query, I say this section of 8 is equal to this section of 8, and this section of 8 is equal to this section of 8, right? For this number, we can decompose it into two potentially overlapping, or no, they will overlap, because if it is a power of 2, then you'll just pick that guy. But like, yeah, two overlapping powers of 2, right? The largest power of 2 that is less than or equal. And do we all agree that now we can still solve this problem, right? Like, doing this query is equivalent to doing these two queries only on the powers of 2, right? This is the same thing of how, this is like literally how a IMQ works, or a splash table. Now, well, I guess I haven't explained anything about how it works yet. So now we just want to do this power of 2 query. So what I'm going to do is I'm going to keep a logarithmic number of DSUs, right? And each one of these DSUs will represent